So in this section we'll be discussing rolling bodies like cylinders, rings, spheres, and the direction of friction acting on that. So say this is a round body like a cylinder or a sphere or a disc, and it is rolling on a hard surface. Now what we are going to study is the relation between omega and the velocity of the center of mass of this, which is v. Whether it is the center of mass or not, it is the central point of the body. So even if it was a disbalanced body, it is going round on a solid thing. This is a solid rigid body. The center will be going with the velocity v. So velocity of the center is v. And what is the relation between them? So suppose it is not slipping. I hope you already know this relation, so I am just going to give you a very quick recap. So say in t time, the angle covered is omega t. So that's your angle covered. So this would have gone forward, and this point would have come on the ground. This arc length L would be equal to r theta, where r is the radius of this body. So that is your r times omega t. Now if this arc length is r theta and this point would have come down, then this central point will be still vertically above. So this point has come down and the central point will be vertically above. So the distance gone forward would be equal to your L itself, that's the arc length, that much of distance this would have gone forward. So the velocity would be equal to L by t, which is your r omega. So this we already know that in a pure rolling, your V is equal to R omega. That's the main relation between V and omega. Now cases when the body is either slipping or skidding. So one of the cases is called skidding, one is called slipping. So you don't have to bother about the name. In one, V is more than R omega. In another case, V is less than R omega. So let us discuss those cases and see what is the direction of friction in those cases. So case 1, when V is greater than omega R. So what's happening over here? It has got a large V but a small omega. So it's not rolling much, but it is just slipping on the thing. So say a car wheel on a slippery surface, so you have already applied the brake and the rolling is not happening, but still it is just due to its inertia it's going forward. So it's skidding or slipping, it is slipping and not rolling much. So your V is greater than omega R in this case. What is the direction of friction? Now the direction of friction, either you can start imagining like what is happening to this point which is trying to rub with this point. So how they are trying to rub, and the friction will always try to oppose the rubbing. The friction always tries to bring the two surfaces which are rubbing to a state of not rubbing. So in your static friction acting, like this was the case of pure rolling, here the point on the body and the point on the surface are not rubbing. They are just, it is pure rolling and they are not rubbing, they are not having any relative motion between the two. The point in contact, the points in contact are not having a relative motion. So that was your pure rolling. Here, either this point is going forward or back. So one is you can invest some time and think where it is going. So you can do that, but I will not ask you to do that. I will rather ask you to imagine this way, that the job of friction is to bring about pure rolling. Friction acts in a direction such that pure rolling is achieved. So that's the big take of this section which I am going to discuss with you. So friction had two options of acting on the body. I am not talking on the ground. On the ground, the direction of friction will be opposite. The friction can either act forward or it can act backward. The friction has to act because there was rubbing, because it was not pure rolling, it was not static. so the friction had to act. So it can either act forward or backwards. If a friction acts forwards, what will happen to the velocity of the center of mass of the body? So before I go into that, one thing, let me make it very clear. If you have any body and a force F is acting, if force F is acting at the middle, force F is acting at the bottom of the body. We know that the external force is F. We know the equation would be F is equal to ma. Here also the equation will be F is equal to ma. See, the mass is same, it is the same body, the forces are same. I would like to ask you what this acceleration is of which part? Which part is accelerating with A? So Newton's law of Newton's law of motion is only valid for the center of mass. So whether the force was acting here or there, the acceleration, this acceleration is of the center of mass. This acceleration is of the center of mass. So maybe if the force is acting over here, this part will be going a lot forward with a greater acceleration, say A dash, this part will be going with a smaller acceleration, A double dash, but the center of mass would be going, this part will be coming, may not be having a forward acceleration, but the center of mass will have acceleration given like this. So irrespective where it was acting, this A acceleration will be of the center of mass. So here the force F is the external force, the friction is the external force. So what will that do? If the black force was there, then what will happen? Your V will become greater. V will become increased. And what will happen to omega? What will happen to omega is your F will create a torque backwards. So the torque created by this F is backwards and the omega will reduce. Omega will go down. So V will increase, omega will reduce, which is not going to bring about pure rolling because V was already high and this F, black F, is increasing it and decreasing the omega. So it is further increasing the gap between V and omega r. So I would rather require a force which increases the omega such that the omega r catches up to V, and extra benefit, extra boon add-on is this force is decreasing the velocity also. So if the blue force was acting, which is the correct one, so I'll just put a cross on this so that you're not confused. So this is not happening, this is not happening. If the blue force was acting, then we get a torque in this direction, which is going to increase the omega, and if this is the external force which is backwards, so it is going to decrease the velocity also. The acceleration will be backwards, so it will decrease the velocity also. The velocity will get decreased. So V was high and omega was down. So now omega is becoming higher and V is becoming down. Both are changing by the same force. So obviously friction will be acting backwards. So friction acts in a direction such that pure rolling is achieved. So you will see that what direction of friction will increase the omega, what direction of friction will decrease the V. So it is doing both the job together. So that's the direction of friction in case when V is higher than omega r. So it is trying to reduce the V. So you can just think of V was high, you want the V to be lowered, so F should be backwards. So that's enough. Now case 2 would be, that's your case 2, when your V is less than omega r. So you may say the V was skidding or something. So skidding is happening over here. Your V is small and your omega is large. Like on a muddy road, the wheel is stuck. You are just rolling the wheel, but it is hardly going forward. So there is a lot of V, a lot of omega, but very less V. So in this case, obviously the answer this time would be that the friction is acting in the forward direction. So what will that F do? F will try to increase the V because F is forward, it is going to increase the V. As well, this F will give you a torque which is backwards. So the omega will be reduced, hence it will bring about pure rolling. So till the point of pure rolling, F will be acting forward. Here till the point of pure rolling, F will be acting backwards. But till the rubbing is happening, what happens is your F is given by mu times the normal reaction. So till the rubbing is happening. Once it has started pure rolling, it's not rubbing, it is a case of pure rolling. So I have written case 1, case 2 over here. So let me put it as case 0 of pure rolling. So in this case, your F is less than equal to n mu times the normal reaction. It is not mu n. it is F, and by the situation you will come to know how much is F, because there is no rubbing, so that formula mu n cannot act. So mu n is only when maximum friction is there, in the case when there is relative motion between the rubbing surfaces. So I hope you have understood where is the F acting. I'll just give you a question and just go through that question, just try to solve that question and see whether your answer is right or wrong, and we'll discuss that. Okay, now try to do this question. You have a cylinder of mass m, radius r, cylinder which is solid. When they say cylinder, you just assume it's a solid cylinder, and you have three cases over here. So A, B, C, you have different cases over here, and you have a case D also. Do all these cases. One is case A is a force F is acting at level r by 2 below the center point. That's your case A. Case B is force is acting at the center. So you have various cases. So case A, F is r by 2 below center. Case B, F is acting at the center at CM level. Case C is F is acting r by 2 above CM, so it is acting over here. Case D is it is acting r above CM. In fact, make case C as r above CM. Case C is your F is acting, that's your case C, F is acting here, that's your case C, r above CM. And case D, where should F act? Where should the force F act such that the friction on the ground is zero? There is no friction required for the motion, so I can't describe it much, otherwise I'll reveal the answer. So what you have to do in all these cases is you have to find acceleration of the body or angular acceleration of the body, any one, and what I will be looking forward is for direction of friction. So this is the main exercise of this question, is finding the direction of friction. So try to get the direction of friction right. Once you have got that right, then the acceleration of the body will be F minus this F minus or plus whatever is the direction of the friction is equal to F plus or minus the friction is equal to mass into acceleration. Acceleration and alpha will be related or not. So if I say that there is enough friction such that pure rolling happens, then you relate alpha and F. There is enough friction. So let me, in all these cases, let me write enough friction such that pure rolling takes place. So try to do the question as fast as possible. In all these questions, what you have to do is you have to write the translational equations like F is equal to ma in at least one direction or both the direction which are perpendicular to each other. So along the motion and perpendicular to the motion. If required, then perpendicular to the motion direction you may write or you may not write. So generally it completes your working when you have written both the direction F along A. So F along A is equal to mass into acceleration along the acceleration direction, and perpendicular to that you write your forces. And the other equation, the third equation what you have to write is torque is equal to I alpha. One equation in torque is equal to I alpha. and two equation in forces generally completes all the set of equations required for such questions. So give it a try, in fact do it. So I hope that you have done this right. Again the concept was V should always be equal to omega times R such that the pure rolling happens, there is enough friction such that pure rolling happens. Even if it is not happening, friction would be in a direction such that this is achieved. Now to make that achieved, the starting velocity was 0, starting omega was 0, meaning to say how much our V is changing, it should correspond to the change in omega. So d omega by dt, change in omega by dt, and dv by dt is nothing, dv by dt is nothing but acceleration, and d omega by dt is nothing but alpha. So your alpha times r should be equal to a such that v remains equal to omega r at any given point. The new v becomes a new omega times r because change in omega in dt time is your alpha, change in v in dt time is your acceleration. So if a is equal to omega r, if a is equal to alpha r, then it will be pure rolling. So that is what the friction will try to achieve. Also one basic what we know is force is mass times acceleration, torque is I about which the torque is acting times alpha. So torque about a certain point creates an angular acceleration which is related like this. Your I is the torque, is the moment of inertia around the point the torque is acting. So in the first case, when F is acting below over there, what do you have a feeling as? What do you think will happen? Now what happens is, what the gut feeling says, that it will try to slip like this, and hence friction should be backwards. Now to get a right feeling of how it happens and where the friction, how the friction acts, to get it absolutely right, what I advise you to do always is imagine that there was no friction. So let me make the diagram as if there was no friction. Your force is acting here, that's F is acting here. Now if there is no friction, then what will happen? Two equations or three equations we may write. One is your mg equal to the normal reaction. This body is neither going down or up. The center of mass is neither going down nor up. So imagining that this is an evenly distributed body, center of mass is at the center, then only we will be knowing the I and all. So of a solid cylinder. Now your vertical equation is N is equal to mg. I am not going to draw the forces, it is just going to cluster the diagram. So that is your vertical equation. Not required in this case unless until you have to get the friction which will be related to the normal reaction. So that's your, in fact, required in this case. So that's your equation number 1. Now equation number 2, what is the acceleration forward? The forward acceleration will be given by the forward force, that is only F, there is no other force. Normal reaction was up and mg was down. That is normal reaction. That's your force arm in the first case, R by 2. Okay. So the force, the only forward force was F. So forward acceleration, which is the only acceleration, is equal to ma. F is equal to ma. That's your equation number 2. Quite a simple equation if there is no friction acting. And if there is no friction acting, then this is the only force. Next is your torque. What is the torque? Torque is equal to force into force arm. So that is F into R by 2 should be equal to I alpha, where your I is half mr square. That's your equation number 3. So these kind of equations you will be making for each cases, but obviously this equation will change, that equation will change with the new force added, which is friction either forward or backward. So this is the case, these are the equations when no friction is acting. So if no friction is acting, let me just compare my A with alpha. Does it match each other as A is equal to alpha R, or is alpha R greater or is A greater? So let me just see. According to equation number 2, what we have is your A is equal to F by M. That's equation from equation number 2. From equation number 3, what we have is alpha is equal to, so I'll just quickly write the thing. So m r square by 2, your 2 and 2 gets cancelled. So you have a m r square over here. So one r gets cancelled. So it is f by mr. So in fact I'll keep one of the r's with the alpha. And let me get my alpha from this equation number 3. So in fact I'll just directly write your alpha. I'll put I as mr square by 2. So your 2 and 2 gets cancelled. One of the r gets cancelled. So what we are left with is m over here. So m goes down there. So you have your f by m times. In fact I'll keep the r with the alpha. So r alpha is equal to f by m. Here a is equal to f by m. So do you think they are matching? No, they are still not matching. They are not matching because of direction. Which way is this alpha? This alpha is backwards. So it is trying to rotate the thing this way. Alpha is backwards, a is forward. So if you are getting, so coming back to the original diagram, if I am getting my a as forward and alpha this way, that is what I am getting. This f is creating a torque this way and a is forward. So are they going to pure roll? No, they are not going to pure roll, because this alpha is going to create, it wants the thing to be going back, whereas this a is making the thing go forward. So they are not pure rolling. So what has to happen is either a has to be backwards or alpha has to be forward. Now a cannot be backwards, because on a body, if you are applying force in the forward direction, friction cannot be generated such that the thing starts going back. That is impossible. So if you are putting the force forward, the body has to go forward. So if the body has to go forward, then your alpha shouldn't be backwards. Alpha should also be rolling. The thing is rolling forward, so it should get an angular velocity in the forward direction. Ultimately, if the thing is going forward, make it blue. If the thing is going forward, then omega should be this way. If velocity is forward, omega should be that way, not the opposite way. The opposite way, it is not going to achieve pure rolling. So that should be achieved. Hence, to make it go forward, what we have to do is, we have to have a torque which is in this direction. So that is not only going to make your alpha forward, it is going to reduce your a also. So what we will achieve is f in this direction is going to help my cause, which is making the a less and increasing the alpha. So reduce a, increase alpha. So anyhow it had to roll forward, then your f had to go back. F had to be backwards, then only your this thing will start rolling forward, because there is no other force to make it roll forward. So what we have is f should be backwards. So that's your first case, case number 1, f backwards. Once we have decided where is f, your decision of f was by working out as if there was no friction. So you don't have to do it, you don't have to write the maths of it, you just have to see that if there was no friction, the body would have gone forward and the body would have rotated backwards. It would have rotated backwards because of F into the force arm, the torque which is backwards. So which is not a case of pure rolling. Going forward means rolling forward. So rolling forward, this F can't achieve a rolling forward. So no matter what, there has to be a friction backwards, which will make our cause right and it will roll forward. So we'll improve this equation and this equation. In fact, we'll change these two equations. So what's the equation now? The equation number 2 in this case will look like your f minus f is equal to MA. Now I can take the liberty of writing A as R alpha so that I can solve the equation. So that's, this alpha is not that alpha, this is the actual alpha, so I may write a dash over here, so that you know that those were when the actual situation is not happening. This is the actual situation, and the other equation is your, so this is your equation in the translational equation for the translational motion, and for the rotational motion the equation is torque is equal to I alpha. So torque will be, the forward torque should match with alpha. So forward torque is F into R minus capital F into R by 2. So F into R is forward and F into R by 2 is backward. So net it is forward is equal to I alpha. I is mr square by 2 times alpha. So those are your equations, and that will give you your answer. So I'll quickly work it out for you. That's your equation number, say 3, the rotational equation. The equation number 1, the normal one is not required. Mind you, F will not be equal to mu times N. So you can't fancy writing the answer with a single equation that F is equal to mu times mg. N is your mg for sure. So that will give you your alpha. That's absolutely wrong. This is not equal to mu n. What's the reason it is not equal to mu n? There was no rubbing happening. We said it is pure rolling. On the onset it was not rubbing. V was 0, omega was 0, and it starts with a very matched up alpha with the acceleration. The alpha matches with the acceleration, and hence it keeps on rolling forward without slipping or skidding or sliding. So there is pure rolling all the time. If there is pure rolling all the time, you can't have your F given by mu n, which is a case when there is rubbing. When there is rubbing, then only that happens. So it's a kind of static friction at any given point. So how to do it? Your R and R gets cancelled. You can just eliminate F by adding the two equations. I'll just quickly do it for you. You may do it yourself. So F minus F by 2 gives you F by 2. Here MR alpha and MR alpha by 2 gives you 3 by 2 MR alpha. So that's your alpha. Alpha is equal to F by 3 MR. So that's your answer. Alpha is equal to F by 3 MR. I hope it is in the frame. So I'm just speaking it out. Alpha is equal to F by 3 MR. Okay. Now if you have got this, apply similar method for your B, C and D and get your answers. If you haven't got this in the first go, just try again. So pause the video and try again. And if you have got your answers and you are pretty sure of it, then just match up your answer with my working out. So for the other situations, I'm just going to rub off your F, and this is what we want to achieve all the time. This is actually not required. Okay, now your case 2. This was your case 1, now your case 2. What's the case 2? Your force is acting at the center, so that's your case 2. The force is acting over here, F is acting over here. We want A, we know A will be forward, so we want alpha this in this direction. That too, your A should be matching R alpha. Now again, this force will be unable to produce any torque. It will just produce a A because it is going through the center. It won't have any force on, so can't produce a torque. So you have to have a forward alpha also. That forward alpha cannot be created by a force which is forward. A forward alpha can only be created by a force which is backwards. So what we see is, if your force was anywhere in this range, at the center and below, then there is no debate. The forward alpha will only come with a backward friction, hence F will be backward only. Now when you go up, let's see, your F will be backward or forward, but at F, your external force being at center and below will always create a friction backwards, because it will always try to drag the body forward. All these forces will try to drag the body forward, and the drag will be felt at this point between the body and the ground, and the friction will be backwards. So what we have over here is, again the first equation remains the same. F minus F is equal to MA or MR alpha. That's your equation for the center of mass. So that's your center of mass. And equation number 2 would be the torque equation. Here the torque is only by F. So F times R is equal to I alpha. So what we see over here is your F, I can just eliminate the F by adding this and this. So we have capital F, I can eliminate friction, sorry, by adding these two. So capital F is equal to, this is 3m R alpha by 2. Mind you, when you are doing these, keep on matching the units. Your alpha should be nothing by time square. So your force is mass into acceleration, m into a. So m and m gets cancelled in the units, and your a by r gives you alpha units. So always when you are doing these questions, try to keep the units in your mind. So what you get, your alpha over here as 2 by 3 F by MR. So it is twice, the alpha is twice this time. Earlier F was trying to have a reverse torque, hence this capital F was trying to have a reverse torque. This time F is having no torque, hence friction can generate more. This friction can more easily generate the rotational motion forward. Hence what you see over here is your alpha will be more, corresponding A will be more. So this body will be rolling faster in case number 2 than case number 1. So I hope you understand why, because your friction is able to generate a alpha in a much better way. So as you keep on going up, maybe we'll have more acceleration and more acceleration. Let's see. So the next answer is, your B answer is alpha is equal to twice of what was earlier. Next is, you are having the force right at the top. So I'll just write your case number 1. So what we have over here is, the force is acting right on the top. Again, the same thing, we have to see whether your acceleration forward matches your alpha or not. So this time you have to be careful with your friction direction. Why? Because your forward force gives you forward acceleration. This force being above the central point gives you a forward alpha. So what we have to see, is it giving enough alpha or more than required alpha? Is it giving more than required alpha or less than required alpha? So had there been no friction, now here that point is quite important. Had there been no friction, what would have been? So I'll just write that. Had there been no friction, so I shouldn't have rubbed the case when I made had there been no friction. So I'll quickly write that case. So that would have given me F without any friction. F is equal to MA. I'm not writing as R alpha this time because I'm not putting friction. The job of friction is to make A equal to R alpha. Without that, it is it is, I would be lucky if I get A is equal to R alpha. So if there is no friction, F is equal to ma, and the torque given by that F is equal to F times R is equal to mr square by 2 into alpha. Now, does the alpha match A? Let's see. So from here, your A is equal to F by m in the forward direction, that is the forward direction, and from here alpha is equal to 2 times F by m in the correct direction. What was required, this alpha is in the clockwise direction, and what we see is alpha is much more, this is R alpha, sorry. So R alpha is much more than A. It is in fact twice of the acceleration. R alpha is twice of the acceleration. Meaning to say what? If you are putting force right on the top, then it is giving too much of a torque. That torque is more than what is required, and your A is not able to match up. This time your acceleration, your linear acceleration is not able to match up with A. So what is going to happen is, you have to have a friction which will assist the A to match up with alpha. So you have to bring your A up and you have to bring your alpha down. So both the thing is achieved by putting a frictional force forward. So if the friction force is forward, it will reduce the alpha because this is giving too much of alpha, and F is not a fixed quantity, it is not mu mg. It can be a very small F which is giving a very small backwards torque, just to decrease the alpha by a tad and increase the acceleration by a tad, so that your pure rolling is achieved and A matches R alpha. So this time the friction will be forward. So if it is right on the top, except when it was a ring, had it been a ring, this I would have been mr square by 2 and you wouldn't have a 2 over here. So luck by chance, your A will match R alpha perfectly. Hence, for a ring, the force over here will create no friction. That would be the ideal case of pushing the body where no friction is required and still it pure rolls. So that would have been for a ring, but for a disc or a cylinder over here, that is not happening. So what we have is F is forward. So the equation would be F plus F is equal to m A, which is alpha times R. Now I can take the liberty of writing A as alpha times R because I know my friction is going to achieve that. Mind you, if it was not pure rolling, and still you have to write the real equation what is happening, that time we'll write A over here, but this F would be mu times n. This F will be mu times n. So still the two equations will be enough to get the answer. F will not be unknown. Your A and alpha will be the unknowns. So, if it is pure rolling, your F is unknown because it can be anything in the range of 0 to mu n. Your F has got a range of 0 to mu times n. It is anything in between. Okay, and in any direction, forward or back. So that's your equation number 1. Your equation number 2 would be your forward torque is due to Fr, capital Fr, and that is being reduced a bit by small fr is equal to I alpha, which is mr square by 2 alpha. So again, to solve this, you just add the thing up and get your answer. So what we get over here is F and F gets added. So, and this F and F gets cancelled. So we have 2F is equal to 3 by 2 mr alpha. Hence your alpha is equal to 4 times F by 3 mr. So you see it is even twice of what was earlier. So you get your alpha in this case is equal to 4F by 3 mr. So meaning to say it's rolling forward more than the earlier two cases, and in fact, if it is rolling forward more, then the acceleration also in the forward direction is quite high. So it is much better than the earlier two cases. Now the last case, where should the force act such that the friction is zero, such that the friction is not required to match up A with R alpha. So what we were seeing is the force was down, the friction was backwards. Force till here, the friction was backwards because something had to provide forward torque. If you go up, then F itself, the external force itself, provides a forward torque. So the friction may or may not be required. So friction definitely is not necessary to be backward. If F is very less up over here, if you have your cylinder and that's the center, and your force is acting only slightly above this, then what is going to happen? In more likely a case than otherwise, this force arm, say D is the force arm, will be too less. So FD torque will be too less to create enough alpha, because F is the same F as earlier, so it will have a certain acceleration. This FD torque will be too less to create an alpha. When F was right on the top, then the torque, FD torque was too much. We were seeing it was too much, too high. But for a ring, it was just enough. For a disc, it was too much. So just going up still has your friction backwards, because FD torque is too less and F has to assist in giving you a forward alpha. But if it is too high, then FD torque is too high. So there must be a point where FD torque is just enough. So we'll call that point as, say, D above, and we'll make the equations accordingly. So situation D, the part D, the fourth part. Okay. So here, that's your disc, that's your center, and say F is acting D above the central point, and this time I am going to take I of any random body and later on put it as a cylinder, so that we have a general idea of the answer. So what I am saying is friction is zero this time, because F is producing the exact right alpha which matches with the acceleration forward. So here A is forward and alpha is this way, and both the things A and alpha is being achieved by F. So what we have over here is friction is zero, so that equation is what is going to happen. F is equal to M. I can write as R alpha because I am saying that it is still pure rolling and F is the cause for it. And the next equation, F, this time the distance between the center, the point of rotation, and the point of application of force is D. So FD instead of alpha, FD is equal to I alpha, I is mr square by 2 times alpha. So I will not write mr square by 2 right now, I will put it later on, a bit later on. So had it been any body, the I of that body, ICM of that body times alpha. So what we have over here is we have to find D. So what we can do is we can just divide the two equations, and what we get is D is equal to, so alpha and alpha will cancel, so we'll have I divided by MR. So that's where the application of force should be. So if it is a disc, your I is mr square by 2. So your m and r gets cancelled, you will have r by 2 left. So that is what we were getting in the first case. You had a distance r by 2, alpha was matching with A, but unfortunately the direction of alpha was exactly opposite of what it should have been. So still the friction was acting backwards because we had to match not only the values of alpha and A, but also the direction of alpha and A. So what we get over here is D is equal to R by 2. So your D, your point of application should be R by 2 above the center. So what does it imply? If your F is more than D, R by 2 above the center, what will happen? your F itself will give extra torque and your friction should reduce that torque and the friction should be forward. So you get the cases of friction being forward if your F is above this magical point, and if your F is below that magical point, if F is acting below this, then what happens? Your friction should be backwards so that it will assist the F in giving a torque forward, and it will also reduce the A, the translational acceleration, so that your A matches with R alpha. So I hope you got the point. So in this range, your F would be backwards, because in this range your capital F is not going to create enough torque. So, and if you are above that range, if you are in this range, then the friction would be forward, because it has to reduce the extra angular acceleration created. So once again, I'll just put the alpha value. Your alpha in last case is F by mr. So alpha is equal to F by mr. So this time it is your forward alpha. So if you have to put these alphas in order, this was the least when it was acting down. When it was acting over here, it was much greater. So greater than the first case, it was rolling more easily forward. If it was right on the top, then too much of alpha. So that was 4F by R. If it is right at the right exact point, it is F by R. So it is 3F by 3mr, you can say 3F by 3mr. So you say 1 by 3, then 2 by 3, then 3 by 3. When it is here, it is 3 by 3, and when it was on top, it was 4 by 3. So you can just analyze how alpha increases, and if I say it was a sphere, a solid sphere, can you just quickly tell me where is that magical point above at which there will be no friction, above which the friction should be forward, and below that the friction should be backwards for a solid sphere? So what do you think? What will be that magical point for a solid sphere? A solid sphere, I is 2 by 5 mr square. So in questions where they have given force acting at a certain point, they are not going to tell you what is the direction of F. You have to take the direction of F correctly. So you just remember this thing, that it is I divided by mr is the critical point. If the force is acting way above, if it is acting above that, then your friction has to be forward. If it is acting below that, then your friction has to be backwards. So you have to choose the direction of friction correctly if you have to get the answer right.